So let's continue talking about our penny demo, but now we are a little bit more informed in how we can progress. Remember, the penny demo is our phenomenon for Unit 4, where we're investigating the interactions, not the bonding, but the interactions between molecules, okay? Individual molecules that is highly dependent on your Lewis structure and molecular polarity knowledge, okay? Yesterday, we got introduced to 3 types of IMFs that are dependent on the character or the structure of your chemical. What was the first type of IMF that we were able to do, that we examined? And what about it? What's some characteristics about it? First type of IMF. Mika!
It was London.
London what?
It was London dispersion force.
Okay, London dispersion forces. What about London dispersion forces? So we have one type of IMF is London dispersion. Shorthand is LDFs, just for shorthand. So I'm just gonna write the shorthand just to save my life a little bit. What about London dispersion forces? What do we know about? What type of molecules experience London dispersion forces? What is London dispersion forces based off of? It's a type of interaction that can be experienced between molecules. What must be true about the molecules? What is it based off of? Liam? Particularly what type of electrostatic attractions? Think about permanent versus non-permanent. How long? What was the terminology we used? Look in your notes. Look in your notes. Temporary, instantaneous. So LDFs are all about instant, random, temporary, right? Electron attraction between. Okay, between, and it's actually electron attraction to the other molecule's nuclei, to like the other molecule's positivity, right? It's instant, it's random. So what type of molecules experience LDFs? Liam? Literally all. Like it is the tripping bar of interaction. Like it is just your basic, you're here, congrats, you have this inherently because you're a molecule. And if you're near another molecule, boom, you've got LDF. Like, okay, if you're a lone island wolf molecule, okay, maybe you don't have LDF because you're alone. Okay, but no molecules exist alone because that's just not how it works. Like, there's not a single molecule in this world that's the only, it's not like molecules go extinct. It's like, and this is the last of its kind in the universe. Like, save the hydrogen molecule. Like, right? It's like, no, it's just there's multiple of them. Maybe not as abundant as other molecules, but there's always more than one. And those molecules are also always surrounded by other molecules. It doesn't have to be the same molecule. It could be one molecule of alcohol with one molecule of water. Like other molecules can mix, hence why we get mixtures, right? So it's just saying that if you're a molecule near another molecule, you're gonna have LDFs, London dispersion interactions. And this is what the weakest, strongest, or middle type of interaction. Weakest. Again, bare minimum. Okay. Okay, what's the second? Oh, one thing to note though about LDFs is there's one particular type of molecule though that is limited to this. Which type of molecule is limited to only experiencing LDF, Mary? Non-polar. Non-polar stays at the tripping bar qualifications. Like it's kind of like that worthless sack of a person in your team that you're just like, you're here, you're not helpful, that's all you are, right? We've all had those people on our team. We've all been those people at one point in our team because we had like bad weeks or whatever, or we don't understand what's happening, right? So all molecules experience LDFs. Okay, non-polar molecules only can experience LDFs. So when we look at our 3 substances, going back to the penny demo, you guys tested out 3 unknown substances that you are now going to use your IMF knowledge to identify and explain what's happening at the particle level. We already were able, We already were able to identify one of them yesterday as water because of the unique boiling point, 100 degrees Celsius. We also were able to properly match based off of, I use class average drop, you're using your average drop number. We were also able to properly match what boiling point goes with which unknown substance based on drop number. And we were able to figure out the higher the drop number, the higher the molecule interaction, the more energy that would be required to spread it out to boil, therefore the more or higher boiling temperature. So we were able to determine that substance 3 was the 100 degrees Celsius boiling point, substance 2 was the 69, and substance 1 was the 78. And again, if your data does not create these trends, you can't lie about your data. All you can say is something went wrong. This is what I got. This is what I know should have happened. Explain why. Okay. But that's where we kind of found ourselves. And now we're kind of going into, well, for this activity, we're being asked, okay, using my IMF knowledge and new knowledge I'm going to give to you today about how we can directly explore several physical properties of substances based off of IMF understanding, based off of particle interaction understanding, we need to create a model, a particulate diagram showing what we know is happening between these molecules and identify the type of intermolecular forces to properly identify which substance is which substance is water. We figured that out, substance 3. But which substance is hexane, which substance is ethanol? We're going to try to figure that out. So based off of our Lewis structures and molecular geometry, we're able to determine the type of IMFs, because if IMFs are dependent on nonpolar versus polar, and that special one that's like a bond, which is dependent on having a specific structural feature of H attached to F, H attached to O, H attached to N, then you definitely need to know the Lewis structure. So based off of this Lewis structure, what can we say for both of these molecules? They definitely have what type of IMFs? LDFs. Okay, so I'm going to write this has LDF, this has LDF. Okay, so that matters because we also know if it only has LDFs, we can expect it to have only the weakest, right? IMF. And that might help us from the negative aspect, not figure out who has the strongest boiling point, but maybe who has the weakest, what substance that might be. Okay, what's the second type of IMF that we talked about? Dipole. So we're going down, increasing. What's some characteristics of dipole? Yes, Aislinn. Yes, it's between polar covalent molecules. Okay, so it's between polar covalent molecules. How do I spell polar? Gee willikers. Polar molecules. Okay, because a dipole means I have partial charge regions. Dipole of one molecule goes to dipole of another molecule. What's really important when we do dipole? What suddenly matters now about dipole molecules? When we were drawing the particulate diagram, what do we know about how the dipoles align? It's in what way do the dipoles align? Think about, if I were to draw a picture, how do I arrange the dipoles to show dipole? Opposites attract. So here with dipole, the position matters in terms of opposite attract. So when you draw and consider dipole IMFs, you want to make sure that your partial positive in one molecule matches up with your partial negative in another molecule. Okay, kind of like saying your left and your rights go together. And when you are asked to get into a line, your left foot should be near the person's right foot, the other person's right foot, right? There's just a certain order if you're supposed to be in a line. Position matters. If you face off each other, that's not a line anymore. Okay, so position matters. So looking down here at our molecules now, What molecules between, or sorry, not molecule. Well, yes, what substances, a vast amount of the same type of molecule, what substances possess dipole-dipole IMFs? Which out of the three possess dipole-dipole, are polar? Which out of the three now also possess dipole-dipole on top of LDFs? Roman, do you know? Think about polar. Which of these three molecules, hexane, ethanol, and water, have polarity in them? How do I identify whether there's a polar molecule? What's a big giveaway that it's polar? Asymmetrical, which is indicated through Mika. Lone pairs on some central atom. Now, if you're like, there's not a central atom, well, we can do relative central. We could say, relatively speaking, okay, there is, okay, a relative centrals. Like every carbon in hexane is a relative central atom if we look at each carbon, okay? You could also think about whole molecule wise, is there just an area that tends to have more negativity around it? So looking at this, what two molecules demonstrate polarity? Either asymmetry or just a general region that seems more negative. What two? I'm going to go back to you, Roman. What two? So could you tell me which ones demonstrate polarity?
Ethanol and water.
Ethanol and water. So perfect. So ethanol also has dipole-dipole. Water has dipole-dipole. And last time we even labeled water as the excellent example for polar. Okay. Oh gosh. And of course, water has an LDF too. Water's got a lot going on. Okay. What would this look like polarity region wise if I were to highlight my partial charge? On this part of the molecule, we're seeing a kind of really negative region. Oxygen has two lone pairs and oxygen is just highly electronegative. So you're seeing this kind of region of negativity, all right, across the molecule. And really what's happening is the molecule, if you were to shade out the positive and the negative, kind of looks like this. Water, you got your two positive regions, and then you've got this chunky negative region in the middle. You've got partial charges, right? You've got an uneven, asymmetrical distribution of positivity and negativity. And remember, if I were to draw out the water molecule 3D, it literally looks like a claw. It doesn't look like this perfect mirror shape like we draw in Lewis structures. It actually looks like a claw. So one half of the claw is more positive and negative, and the other half is more negative than positive, right? Okay, so why doesn't hexane have dipole-dipole? Can you explain why it doesn't have dipole-dipole? What must be true about hexane as an entire molecule? Hallie? It's non-polar across the whole thing. And you're like, how'd you know that? It is literally all carbon H bonds. Carbon H bonds are a 0.4 electronegativity difference for carbon H. So I have, first of all, a giant non-polar bond, okay, making up a giant molecule that is symmetrical with no lone pairs. So we know something about this molecule. The whole molecule is non-polar. Yes.
What if one of the bonds was polar and one of the bonds was non-polar?
If it was symmetrical, it could still cancel out.
So if it was symmetrical, you would still call it non-polar, but if it was asymmetrical.
Yep. It kind of depends on the giant structure. You'd have to account for each relative centrals. You'd have to analyze each carbon. Yeah. If it had a different terminal atom, you'd have to go bond by bond. We will not ask you to do that. Yeah. Well, I don't think we even ask like organic chemists to do that. Like, I don't remember looking at that deeply. Yes.
Will we have access to the electronegativity?
Always. Always. I will not make you memorize the Pauling scale of electronegativity values. That would be cruel and unusual punishment. And I already know that I make you memorize way more than the other classes do. So, okay. It's okay. You're stronger for it. What's the third type of IMF that we covered yesterday? The third type that's really unique. What's the third type of IMF? The strongest out of all of them. Matthew? Yep, look at your notes. Scared the bejeezers out of you. I'm not that scary. Except when I'm super angry. What is the third type of IMF? The strongest. Hydrogen. Is it an actual bond? No. So what do you want to do physically with your hands to show me that you know that it's not an actual bond? Thank you. Tell me about hydrogen bonding. What's must be the case about hydrogen bonding? You're looking at your notes, man. I assume you can read your own handwriting. Let's go. What? Tell me about it. When do hydrogen bonds occur between molecules? Excellent. Between polar covalent molecules with an HF bond or an HO bond or an HN bond. Okay. So what does this look like for H bonding? It would be like if we had ammonia, a polar molecule made up of 3 NH bonds near another ammonia. And what we would see is that the ammonias would orient themselves around each other so that your N was attracting on one molecule, your N was attracting the H on another molecule. And your H on one molecule was attracted or oriented around to be near your N on another molecule. And what you see is with the hydrogen bonding, the H wants to get near the O or the N or the F on another molecule. And the O, F, or N on one molecule wants to get near an H on the other. And it just orients itself around. So the idea of position matters carries into the third IMF, the strongest type. Okay. So looking now at our options below, we all good with this? Looking now at our options below, who has H bonding capabilities? Danny, what'd you say? And ethanol, water and ethanol. Excellent. Have H bond possibilities, H bonding possibilities. Now, if you're like, oh, then they must be equally strong. Well, we know something about our boiling points. They're not all 100 degrees Celsius. So what do you notice about hydrogen structure in H bonding versus ethanol structure in H bonding? How many H bond structural features is in water versus H bond structural capabilities in ethanol? What do you notice about water versus ethanol's H bonding capabilities? They're both capable, but one molecule has a unique structure that really highlights. Can you explain that to me? I see you. I'm just going to ignore you, Aislinn. Jose, do you want to try to figure this out? What about ethanol's H bonding ability is different than water's?
It has more H.
Okay, more H atoms or more? It's not the H atom itself. I mean, all of these have H atoms. It has more H bonding features. Specifically, what H bond? HF, HO, or HN? Where's the HN in here? Which type of it? HO. So in ethanol, I have one HO bond. in my structural feature. The rest of the molecule is pretty worthless in terms of H bonding. So when I line up ethanol with another molecule, I got to make sure that that part of that molecule is actually being oriented correctly. But water is made up of 2 HO bonds. It's like it's double. It's like its whole molecule is just made for H bonding. From both sides, it can H bond. It can double whammy it. Okay. So what does that mean then when we look at these options for the identity of the substances? We already figured out that substance 3 is water. Now we know why. Substance 3 has the highest drop number, the highest boiling point. Can you tell me why water? It makes sense that substance 3 is water with the highest drop number and the highest boiling point. Can you someone tell me in one sentence why it makes sense? Kayla or Wolf. Hallie, sorry. You're different. Yes. Okay. It has the most and the strongest. It has all the types of IMFs, which includes the strongest in the most amount, too, with the greatest structural capability of doing H bonding from all angles. Excellent. So then what must substance 2 be and substance 1 be? What must the identity of substance 1 and 2 be? Hexagon itself. What must the substance identity of substance 1 and substance 2 be? If we know substance 1 had a medium-sized dome and substance 2 had the smallest dome.
Substance 2 is probably hexane.
Mm-hmm.
And 1 could be ethanol.
Excellent. Now, again, if your data does not match this, you need to make a note that something went wrong. If your data does not actually support this, you need to make a note something went wrong. But this is what you should have gotten. And why does it make sense that ethanol is the second largest dome with the second highest boiling point? Jose? Or no, actually Valeria, why does it make sense that ethanol is the second biggest dome with the second highest drop number with the second highest boiling point? Why is it below water but above hexane? Yes, you do. Look at what we wrote about IMFs. It has, we listed the types of IMFs. It has, so if it has H bonding, that means that it has all. If I don't just have H bonding, I have, look at on the page. What do we also have? Dipole, and? Do you know those letters? Perfect. What does LDF stand for? Notes. London dispersion forces. So if I have all 3 types of LDFs, why does it make sense that ethanol is the second biggest dome? It has the second highest average count in drops, and it has the second highest boiling point. What must be true then? Based off of our intermolecular force identification, using the structure of it, the Lewis structure, why does it make sense that ethanol would be substance 1 with the second biggest dome? It has everything, good. So it has all 3 IMFs, but what makes it different than water? Water has, what did we just name about H bonding versus H bonding in water? So water has, which one has 2 bonds? I don't know what 2 bonds means. Water has 2 what type of bonds? Great, but ethanol only has. So why does it make sense that ethanol is the second largest dome? It's the second highest in IMFs. And the biggest distinction is that water has two H bonding structural features versus ethanol. Good, good. Okay, so then ethanol, if we were to draw a particulate diagram of ethanol, okay, remember everything about particulate diagram is strategic. So I don't want to necessarily draw every single atom for all of those atoms. Like that's going to be a very long particulate diagram. So maybe what I'll do is I'll make this be equal to my C2H5 portion of my ethanol molecule. And I'll maybe make this be equal to my OH portion of my molecule, particulate diagram. And I'll make that a little smaller in a circle. So it represents that that OH isn't the biggest part of the molecule. And maybe what I'll do is for drawing a particulate diagram of ethanol is I'll delete, copy and paste a couple of these in here. And then what I got to do is I got to orient them. My OH is going to orient around so that it's close to my OH on another molecule. Okay. And my I got to orient this around. Oh, maybe make it a little bigger. Little gee willikers. Okay. Maybe. Why does it hate me? Let's go. Oh, okay. Okay, whatever. It's fine. There you go. Okay. Oriented around so that my OH is around, right? Positioning matters. Maybe that's what I would do. I don't know. You can choose. You could do a star. I think that'd be weird, but you could do a star. You could do a hexagon. I don't know. I still think that'd be weird. Okay. But my particulate diagram should represent how these orient themselves around. And notice my my C2H5 section is also closer together because they're going to engage in LDFs more. It's like an LDF region, okay? A non-polar region, right? So maybe I'll just do-do-do-da. Oh, that went, what in the world? Help me. Help. Okay, well, we're just going to delete that and say that it worked. Fan and dandy, okay? So maybe that's how I would draw my particulate diagram to show what's happening. Yes. To represent that for my particulate diagram of ethanol, it represents the two C's and the H5 region. But the OH region is the green part. So I can highlight the different parts of the structure. Okay, so then hexane, it's the smallest. Maybe what I'll do is I'll just make it one big chunk because it's all non-polar. And is there really a position that matters? Not really. It's just kind of like around each other. So maybe that's what I'll do is my little circle, my rectangle here is just C2H5. Now, why didn't I care to make to show the different types of atoms? Because in the end, it doesn't actually matter. It doesn't play a role. The difference between C and H doesn't matter to me in terms of demonstrating what is important, what's happening between these particles. No difference. The C is not going to align itself with another H. Like it doesn't matter. That's why I'm not stressed about showing every atom for this particular particulate diagram because it's not essential. Your particulate diagrams are with intention. They include the information that you want to include, and they don't include the information that you don't care about. That's irrelevant, right? Yes.
I don't know if someone already asked this, but why are they both C2H5?
Nope, that is just me having a brain fart. Thank you. C6H14. Okay. Okay, so I relatively well showed that they're liquids because all of the particulate diagrams have a substantial amount of particles being represented, but somewhat spaced out. I showed positioning. Size, kind of does not matter. I did show a little bit of size difference between the OH in the ethanol versus the C2H5 chain, right? The big trick here though is water. Water, water, water. What's wrong with my water particulate diagram from yesterday? Yes.
They are.
Yeah, they're not positioned correctly. Right now, I have oxygen kind of close to oxygen. That's not how it works. So what we're going to want to do, and if you are non-digital, this is going to suck a little bit for you. We're going to want to orient all of our waters. How do I orient this sucker? Around so that my hydrogens are closer to my water, or sorry, my oxygen in another molecule. And my oxygen is closer to my hydrogens. Right? And so we're going to kind of want to, we're going to kind of want to play around. Oh no, with this. Okay. And it's not going to be super perfect, but you know, yeah. Mickey Mouse won't turn. You could do it with different colors. I'm not because I'm too lazy, but. And so I want to make sure that my partial negative oxygen region, symbolized by the dark circle, bigger atom, is closer always to my little ears, my Mickey Mouse partial positive hydrogen regions on another water molecule. Okay. Sounds silly, but this makes a difference, right? If we're trying to understand the particular nature of the world and suddenly positioning matters, that makes a huge difference for chemists understanding how the world works, right? It's like saying that, oh, I want you to line up versus I want you to create a window form from cheerleading, right? Where you alternate, you're in between the people in the next row. That's a different structure. That's a different format. It does change, right? So that's what we kind of want to highlight. Yes.
So for ethanol, why do OH want to be close to each other versus in water, the different elements want to be?
Well, technically the different elements do want to be close to each other. I just didn't. If you want to, you can even get more. If you can tack on a little H at the bottom, if you want to. Like you could do that, tack on the little H.
Because the O and H are.
The O on one molecule is attracting the H on another molecule. The H on one molecule is attracting the O on the other molecule.
So the light green is not technically attracted to the other light green. It's attracted to the black.
Yeah.
The black dot.
Or it's like a bluish dot.
But not the clump of black.
Yeah, exactly.
But why not?
The clump of black is C2H5.
So doesn't.
It's totally, if we just were to cut off the OH, that would become a non-polar structure, right? If I were to cut off,
Oh, right, yes.
and I'm not exactly attracted to, if I'm a polar molecule, I'd rather be with another polar molecule.
Right, but if it was just the non, okay, never mind, I get it.
Got it? Cool. So there you go. You have a particulate diagram where you were able to correctly, hopefully based on your data, identify the type of substance for each penny that you tested and explain why your data makes sense, why you had a bigger drop number, why you had larger boiling point based off of the structural IMF features, right? Remember, structure determines function. The structure of your molecule determines how it works in the world, okay? And so that's what we're gonna hop into now into notes. What are some other physical properties that we can describe other than boiling point based off of IMFs? So switch over to notes, and I hope to be done with notes in about 20. So let's switch over. And what we need to look at is how now do we take our particle microscopic understanding of IMFs to explain all the physical properties, the functionality of substances. So let's just start with really easy category, states of matter. Why do we see at room temperature different states of matter for different substances, right? Like why is oxygen gas a gas? Why don't we just drink oxygen liquid? which is super combustible and would definitely kill you. Okay. Why is your butter solid for the most part at room temperature? Maybe a little soft, but relatively solid. But why is your olive oil liquid? Right? You hope that your ketchup is also liquid or your milk is liquid. If it's chunky, that's a problem. Okay. Why is your milk liquid? Why doesn't your milk immediately solidify when you put it in the fridge? All of these things, like why do we see what we do? So states of matter, first of all, let's start with the highest energy state of matter. Gas is the highest kinetic energy, okay, between particles, state of matter. So if we were to draw a particulate diagram, they're like everywhere, man. Their vectors are going everywhere to show their motion. High energy, long arrows. They're kind of far apart because they're spreading out, big volume, right? Gases have the lowest IMFs because they have the least interactions between molecules. If I'm far apart and I'm moving past you, okay, even if I collide with you, I'm probably not going to stick to you very well. I'm just going to, you ever get like completely run over by like your dog or something and they just like bust through you? I've had my dog like jump on me and push me down the stairs. The dog was fine. I was not. Okay. If you're moving at a fast enough speed, like I don't know if any of you guys have seen me run back and forth to the printer. Okay. I bump into a child, I'm still going. The child and I are not staying like attached. Like I'm moving past them. Very little interaction, very quick. Same thing with gas molecules, high kinetic energy, low interaction, very low IMFs as a result. Notice this is not about types right now. It's not about types right now. It's just about strength in general. In general, it's not quite about types right now. I could have a molecule that has like all alcohol, like all drinking alcohol is an alcohol group of OH, which means it's capable of H bonding, but it's still liquid at room temperature, right? So types of IMF does not directly correlate to what state of matter you have to be in. It just is used to explain maybe comparatively why we see certain states of matter, okay, for certain substances. So liquids, on the other hand, okay, they are, I know this is like super kid language, but like mid kinetic energy, like average kinetic energy between particles comparatively. And they have mid IMFs. So they have some interactions between the particles. We call them very fluid interactions, which is, by the way, why your liquids take on shapes of containers. So if I were to draw a particulate diagram, I draw some motion, but I draw the particles a little closer with a little bit less, okay, energy, smaller arrow. I really hate physics, but for some of you, this is like a nice break, Liam. So solids, as you can imagine, then are the like very almost no kinetic, super low kinetic energy between particles. Okay, super low kinetic energy between particles, super low. Oh, actually not low IMFs, super high IMFs. High IMFs. Here's why. If I'm moving super slowly, like moving through like mud, it's way easier to get stuck, right? Someone can catch you, someone can cling onto you, the Velcro can stick better, whatever you want to think about the analogy. So you have actually super high IMFs between solid particles, and you have a lot of interaction then. And we say that the motion is vibration motion because all the particles do is they like, it's like shivering. They like shiver against each other, okay? So what you might do is you might draw structures of particles super close together, just vibrating, okay? So that's one area of properties, one category of properties that we can use IMFs to explain. We can create a correlation between them, okay? Or did you just, okay. So I don't want to go over this example problem right now. We'll warm up with this tomorrow. Let's move on to the other Okay. Ways that we can analyze. Let's move on to mixtures. How can we use IMFs to explain different mixtures? Okay. And we're going to look at gas, solid, and liquid mixtures. Okay. So first and foremost, you need to understand a few key terminology about what a mixture is. We can have a non-mixture, which is known as a pure substance, all same chemical species. Okay. So like a really good example of pure substance is like a glass of water. It's all water molecules, right? A glass of water is the same pure substance. A glass of milk, all the same molecules, right? And then we have a mixture, which is two types, okay? So when we say what a mixture, it involves two or more types of chemical species. And then within that category of mixtures, we have two types of mixtures. We have what we call a homogeneous mixture. Homo meaning same, right? One, where the two or more components are evenly distributed or mixed. Okay, appearing like a pure substance, appearing like a pure or looking like a pure substance, maybe is a better way of saying it. Looking like a pure substance. So an example of a homogeneous mixture, which is called solutions, that's our AKA name for a homogeneous mixture, is a solution. And it's just another name for homogeneous mixture. A really great example is your coffee and sugar. Your coffee or creamer, maybe that's a better one. Your coffee and creamer. Your coffee and creamer is a great example of a homogeneous mixture. Two different components that when you mix them together, take on a look of being one type of thing. We have a way of labeling that, by the way. Its solute is the chemical species in smaller amounts. So that would be the creamer would be our solute if we're trying to label the two components in the mixture. And our solvent would be the coffee, the species in larger amount. That would be our coffee. Oftentimes, water is our solvent. So when we have a mixture where water is the solvent in a solution, we call that an aqueous solution. And the symbol for aqueous is AQ with a parentheses around it, AQ. That's how we symbolize it's a water-based mixture. So what does this have to do with IMFs? Well, how do you think these things mix? The particles of your solute start interacting with the particles of your solvent, creating an even particle distribution where they all interact. So what we have here is not just an even particle distribution, okay? What we really have to say is due to IMF interaction. That's the big thing right here. It's due to the IMF interactions. If your particles just stay separate, there's no interactions really. There's no mixing really. There's coexisting in the same space, but that's not necessarily mixing. Okay. A really good example of, so I gave you a liquid example of a solution or a homogeneous mixture where the IMFs of one type equally or evenly interact and distribute with the IMFs of another particle. Okay. But a really good example is we can actually have this happen between solid mixtures known as metal alloys. And these are just a fancy way of saying a solid homogeneous mixture. So for example, your brass and steel are two solid mixtures where the particles interact with one another through IMFs and some metallic bonding. Sometimes it kind of goes hand in hand with certain metals are weird. Okay, to create a seemingly one type of looking metal. Like you would never look at brass and be like, oh, it's made of several things. Like you'd be like, no, it's brass. It's like, it looks like one thing. I could not pick out the other components. Okay. We can also have this with gas solutions, which is, by the way, air. Okay. Gas solutions, please pull out a nitrogen atom for me versus an argon atom for me. Right? So we can see gas solutions. So it's a gas homogeneous mixture. And how do all of these mixtures occur? Through the IMFs between the particles, right? So an example is your air. And all of this occurs, again, due to the IMFs between the particles. All of this is possible. Now, I have to mention the opposite type of mixture, which is a heterogeneous mixture. Can anyone guess what the definition of a heterogeneous mixture is? Just modifying the first definition a little bit. Yeah, Aislinn?
Two components that are not equal.
Excellent. The 2+ components are not evenly distributed or mixed. Okay, so you can actually see the individual parts. So a really good example of this is trail mix. I can pick out the dried fruit. I can pick out the M&Ms, and I don't exactly have a deep concern about me having my peanut be merged into my like dried raisin or whatever. Okay, it's trail mix or salad. Salad is a great homogeneous or heterogeneous mixture example. You can see the different components. And by the way, each component retains its own unique properties. You don't look at a raisin in a trail mix and be like, oh my God, it tastes like a peanut. Like, no, it's still the raisin, right? So let's take this now and take an example of a walkthrough of how we can break down the IMF interaction between a solution. Because really, solutions are dependent on IMFs. Homogeneous mixtures are dependent on IMFs. Heterogeneous, not so much. So let's break down a homogeneous mixture that is very common in chemistry. It's called ionic compound solution homogeneous mixtures. And there's actually a particular name for this type of mixture. It's known as dissociation. Dissociation is the process of an ionic compound forming a homogeneous mixture with water by breaking up into its individual ions. Okay, so before I get too far into this, you should make a note to yourself that this is a very unique type of IMF. This is your bonus IMF, your fourth type. This is your bonus fourth type because it doesn't quite perfectly fit into IMF definition, but it also doesn't fit into bonding definition either. It kind of just exists outside of it all. So what we say is that polar substances like water, okay, can form attractions with the fully charged ions in ionic compounds. Okay, with the fully charged ions in ionic compounds. We call this a formation of, notice the lack of creative naming, ion dipole attractions. An ion from my ionic bond is attracted to a partial positive region or partial negative region in my dipole polar water molecule. Yeah. So what we do is we say we form an ion dipole attraction. How does this occur? The partial, and I'll even color code this, the partial negative region of my water is going to be attracted to a fully charged positive cation in my ionic compound. So what will it do? It will orient itself so that the water's partial negative region surrounds my now separated ions, fully positive area. And what we say, it actually creates a hydration shell. Because remember, if water's the solvent, it's in a lot more amount. So it's kind of like I have excess water and my water molecules will just kind of orient themselves all around. Orient themselves, goodness gracious, themselves around, the positive cation. Okay. So what you see is that we call this a hydration shell forms. Okay. Via hydration shell orientation. Okay. And notice position matters. My partial negative aligns or orients around the fully positive cation. Okay. Hydration shell formation. Okay. And then, so what would you imagine then the negative anion in water would look like? What would the hydration shell look like now for the negative ion in water? What would my hydration shell look like for the negative ion in water? How would we flip this? What would I have said, Aislinn? Excellent. So now the hydrogens want to be super close to the super negative and anion, a negative ion. So what we do is we would say that the water molecules in an ionic compound dissociated aqueous solution where water is the solvent, we would say, good God, that the hydration shell of water would now orient itself. It froze. Orient itself around, it froze, the anion so that the partial positive, region of water is around the negative anion. Right? Does that kind of make sense to you guys? You see? Which is, by the way, a type of IMF. It's one molecule interacting with not another molecule, but another particle, an anion or a cation. Why will this thing not turn for me? Why does it hate me? Okay, so anyway, you get the idea because I can't seem to get this thing to turn. Maybe if I copy and paste. Copy. There we go. Will it turn? Okay, idea made. Does that make sense? Okay, I love how that's the worst question a teacher can ask you. Does that make sense? And you're like, I don't know. And then you just nod your head anyways. So if I had to describe the before, during, and after, what would this look like? Well, before we have our solvent to solvent IMFs. And we have our solute to solute IMFs. And actually, the solute here would be the salt. So what's actually really unique, it's not an IMF. I apologize. It's an intra molecular bond. It's your ionic bond. Intramolecular bond is just another way of saying an actual bond. And then we'd say that during, so this is the before, the during, what's happening during is that you're breaking your solvent IMFs and you're breaking your solute ionic bonds, which is again why this is a unique category. It's not just IMFs being involved here. It's an actual bond being broken to then engage in a specific type of IMF. And then after, what we have is solvent to solute. Solvent to solute, where my solute is my ionic compound ions, right? The ions are the solute. Solvent to solute ion dipole attractions, which are a very specific type, right? Type of IMF. So here, ionic solids are not based on intermolecular forces, but are the result of an ionic bond. But we're creating an intermolecular force when we separate the ions in an ionic compound in water. This, by the way, phenomena only occurs with ionic compounds in water. This would not occur with like other types of compounds. That's why I want to take a couple minutes to say how unique it is. And it's a really good example of the idea of how IMFs are super important and how they can interact with bonding, but they often don't. But you'll see this unique crossover. Okay, so let's just go through the final really simple topics of properties. And then tomorrow you'll get time to work on your CER after the quiz. Tomorrow you'll have a quiz on on IMFs in general. Okay, being able to identify them and explain certain properties based off of the type of IMFs you identified. Okay, so surface tension. Let's look at another property, another category of physical property. Surface tension is the resistance of substance to increase surface area. So higher IMFs, more surface tension. I'm going to say ST for surface tension, okay? Viscosity is the resistance of liquid to flow. Higher viscosity, higher IMF. Okay. And then we have one final type of unique solid that demonstrates IMFs. It's a molecular, which means covalent, bonded solid. Covalent molecular solids are formed from molecules engaging in IMFs, engaging in strong IMFs. So like a really good example of a molecular solid would be like sugar. Okay. So what are your tasks for tomorrow and expectations on knowledge of IMFs? One, you should know how to use IMF information based off of Lewis structure and molecular polarity to determine and explain physical properties. So use this information. That means IMFs based on Lewis structure and molecular polarity to predict and explain physical properties. You should know the relative strengths of things. So like intramolecular bonding, like the actual bonds that we talked about, ionic, covalent, and metallic, are always going to be stronger than your between molecules. Kind of like how you hope that like if you get punched in the gut, your guts don't spill out, but if maybe you get punched in the hand, maybe that penny will fly out of your hand, right? How the outer interactions with the world are always weaker than the inner interactions that hold you together, right? You should also know that ion dipole, remember, is a very unique type of IMF. It kind of flows between bonding and interaction between molecules. All right. Honors, you have your honor solubility and ideal gas law stuff coming up. So that's your responsibility. Honors, just so you know, you definitely will be quizzed on solubility tomorrow, but it's really easy. So you will be quizzed on solubility tomorrow, but it's way easier than you think. And I've already introduced half the concept in class. Okay, so honors, you will be quizzed on this tomorrow. All right, guys, good job.